Okay, we're going to go over pi and specifically a proof of pi. So pi helps us find the circumference of a circle, the area of a circle, many things like that. And what we're going to do is we're going to compare it to shapes that are essentially similar to the circle but have specific numbers of sides. So, for instance, we have a hexagon inside of this circle and another hexagon outside of this circle. So, in order to have an inequality or a proof for this, the perimeter of both of these hexagons, the one on the inside, will be less than the circumference of the circle, and the hexagon on the outside will have a perimeter greater. So we're going to set up an inequality. We have circumference of a circle is 2 pi r, and we know that the perimeter of the outside will be greater and the perimeter of the inside hexagon will be less than that. Okay, so we're essentially going to set those up. What we have to do is we have to figure out what the perimeters of both of these circles are. So I've actually split them, and I'm going to get rid of the outside one right now. Oops, wrong button. Okay, so let's get rid of that one. So what we're going to do is essentially, because this is a regular hexagon and these are touching the inside of the circle, all of these distances are equal to the radius of the circle. Okay. So there are 6 sides to this, and we need to find out the angles inside all of them. Or specifically, just one of the triangles will be the most helpful. Now we know altogether this will equal 360. Essentially, you're going around in a circle. So we have 360 degrees. Okay, and because there are 6 small triangles, and we'll count them here, 1, 2, 4, 5, 6. To figure out what the angle of one of them, because it's regular, everything being the same, we'll divide it by 6. Okay, so when we divide by 6, we get a angle of 60 degrees. So we'll use the one on top. We know that this is 60 degrees, and we know that the sides are equal to the radius. So we're going to create an isosceles triangle, and this one actually ends up being equilateral. But the idea is to create isosceles triangles to help us with these proofs. So the isosceles triangle, this part here is essentially this part of what we've drawn in the blown up version. So we need to find out the distance of this. So we know the sides are both the radius, okay, and we know that the angle underneath is 60 degrees. Because it's isosceles, we can essentially split it down the middle. And for our new right angle triangle, this angle is half of 60, so it's 30 degrees, and this one is 90. So we have a distance of the bottom of this. We're going to call it y in this case. So we're going to set up a trig ratio for this. Since we have 30 degrees, we're looking at the opposite and the hypotenuse, which gives us sine ratio. So we know that sine 30 is equal to the opposite, which is y in this case, divided by the hypotenuse, which is our radius. Okay, and I'm going to set it equal to y. So set it equal to y, we'll bring r to this side. And essentially we have r sine 30 is equal to y. Okay, well, to figure out this whole distance, we'll call this essentially x. And we know that 2y will be equal to x. Okay, so in other words, to figure out the entire distance of this x for our perimeter, we have to double this, okay, because we need to multiply by 2y. So we're going to be multiplying this distance by 2. And that will give us the distance of this opposite side of a triangle. So we know that x is actually equal to, and x being this complete distance, and I guess we'll put it in purple so we can reference a color, is equal to 2r sine 30. Okay? And since this is a hexagon, to figure out the entire perimeter of this object, because there are 6 of these, we're going to have to multiply this distance by 6. So this was the inside triangle, right? We need to multiply it by 6. So we need 6 times 2r sine 30, okay, which essentially leaves us 12r sine 30. Oops, sine 30, which is less than 2 pi r. Okay, we still have to find the outside, the perimeter of the outside hexagon. So we're going to take something that's very similar, but in this case it's a little different because our radius, okay, so we'll break them into triangles again. Right, so we're going to have 6 triangles just like before. And we'll speed up our process for the next one. Okay. Now, the only problem with this is all of these corners are outside the circle. So the only thing that's actually considered a radius here, and we'll do it in red, is directly in the middle. Okay, so directly in the middle would be our radius. So again, we're going to create our isosceles triangle outside. So here's our isosceles triangle. Actually, we'll do it in red. Sorry, black, I mean. So we'll create our isosceles triangle again. This one being a little different. That the height of the triangle, or the line going down the middle, is actually equal to the radius. Now, because it's directly down the middle, it's also 90 degrees. So we know this is R. And due to above, again, these triangles all add up to 360. There's 6 of them, so we know that the angle is still the same angle from before. It's still 60 degrees. Okay, so this angle here is 60 degrees. And when we split it in half, this becomes 30 degrees. So again, we're going to create a very similar relationship to figure out what we'll call Z in this case. So we know that Z will be equal to the, and this time we have to reference our radius. So this is the adjacent and the opposite side, okay? So adjacent and opposite gives us tan, so we have tan 30 is equal to adjacent, which is R, right? I should move the Z underneath. R divided by the opposite side, which is Z. Sorry, opposite over adjacent. I wrote that upside down. I knew that's something funny. The Z should be on top. We had to write it first. Okay. And then to isolate for tan, we got to bring the R over, very similar. So we have tan 30R is equal to Z. And again, we're trying to find double that length. So we need to multiply it by 2, just like we had done above. So the entire distance across here is equal to, so this length, we'll call it, I guess we'll call it L in this case, is 2 tan 30, technically times R. So we'll squeeze the R in beside the 2. Okay. And same idea, because in order to find the perimeter of the object, we have to add all 6 sides. We can multiply it by 6. So we have 6 times 2R tan 30, which gives us 12R tan 30. So how is this going to help us essentially prove pi? Well, what we can do is we can reduce everything. I'm going to have to move a couple things over. Because this is an inequality, I'm going to divide everything by 2R. And when I divide by 2R, that will eliminate this 2 and this R, essentially creating 1s, okay? Which means I'm going to divide this 12 by 2, and this R will disappear. And the same thing happens here. We divide this by 2 and eliminate the R. So we're now left with 6 sine 30 is less than pi, which is less than 6 tan 30. And I'm going to need a little more room. So we'll move these things down a bit. And we're just going to figure out exactly what those things are equal to. Get a whole nother line. So we'll take our calculator out. So we have 30 sine, oh, it's in radians, give me a sec here, degrees, here we go. So 30 sine times 6 is equal to 3. Okay, so we know pi is greater than 3, and what is it less than? Well, it's also less than 30 tan times 6, which is 3.46. 3.46. Okay, so we already know that pi is between these numbers, and these are pretty far away from it. So what we're going to do is we're going to get other regular polygons that have more sides to it. And the more sides we add to a regular polygon, the more circular-like it becomes. Okay, so with that being said, we're going to speed up the process. This happens to be a 10-sided shape. Okay, so same idea as before, and I'm just going to focus on one triangle. Okay, we got to find the angle in there. Well, we know altogether, same idea as before, it's 360, and we have to divide by the number of triangles, which would be 10. So that means the angle inside, when we divide by 10, would be 36. Again, we're creating our isosceles triangle. And in this isosceles triangle, because it's inside, same as before, the radiuses are on the outside, just like the very first triangle we'd started with. Okay, we draw a line down the middle. Okay. And because we know that this angle is 36, that means when we split it, the angle there is going to be 18 degrees. Okay, and this is 90. So same idea as before. In order to find this y, we're going to have to set up sine ratio. So sine 18 is equal to opposite over hypotenuse, which is our y, over r. We move the r over, and again, we'll have to multiply by 2, which essentially is going to give us 2r sine 18 is equal to that entire length. We'll call it L1. Maybe it'll help us make more sense of it. Okay. Again, we'll go to the outside one. The outside one, we again have to make our triangle, and this time the radius happens to be in the middle, so we redraw our isosceles triangle. The height of the triangle will be the radius. Okay. This angle we know will be 36, and when we split it in half, 18 degrees. And this time, this is being our y. Okay. We have to set up a tangent ratio. So tan 18 is equal to opposite, which is y, over the radius. And again, we have to multiply by 2, so we'll say our L2 is equal to 2r tan 18. If you're not sure how we did that, it's the same as above. We just kind of moved the r over. So, set up the exact same thing before. Our perimeter we know must be between these two values. And the circle must be, the circumference of the circle must be less than this outer one, but greater than the inner one. So, 2 pi r is less than, this is our outer formula, so 2r tan 18. And it's not just 2, because in this case, remember we said it had 10 sides. So we have to multiply this by a value of 10, just like we have to multiply the other one by a value of 10. And this is our inner triangle, our inner polygon. So 2r sine 18. And we know the circumference is less than that value. So as we go to figure this out, essentially, we're going to, again, reduce this, divide by 2 and r, so that gets rid of this 2r and this 2r, which leaves us with 10 sine 18 is less than pi, and 10 tan 18 is greater than pi. Then we'll figure out those exact values, so we get a good idea with our calculator. So we have 18 sine times 10 gives us 3.09. 3.09. And then our other one, whoops, which is our 18 tan times 10 gives us 3.24. 3.24. Okay, so we're getting closer. We want to try to be extremely accurate with 10. So I use 10 purposely. What if we had, theoretically, a million-sided shape? It would probably look extremely close to a circle. Okay? Well, if you notice, essentially what's happening here, as you notice again above here, we had 2r sine 30, 2r tan 30. Okay, that was before. Here we have 2r sine 18, 2r tan 18. Well, 18 is going to be our degree for a million-sided shape. It's just going to be reduced a little, right, because of our side. So I'll get us our new degree here. And then I'll show you, essentially the idea is this part ends up being the same, and we just multiply by the number of sides to the shape. So if there's a million, and we have 360 degrees, we have to divide it by our million, just like we did with our other polygons. Okay, which means we're going to move this 6 decimals to the left. So that becomes 1, 2, 3, 4, 5, 6. So 1, 2, 3 zeros in front. So our angle inside our isosceles triangle, okay, our angle here, it's all blown up, is actually 0.00036. And because we have to split it like we did before, it actually becomes 0.00018. So that's our little angle there. So we know that the inner one, and this will be our inner. Okay, this is our inner. Let's put inside. The formula ends up being 2r sine whatever our new angle is. And in this case, our angle is 0.00018. And we'll have to multiply by the number of sides, right? So we'll have to multiply this by 1 million. Because there's a million sides, it's 1 million times 2r sine 0.00018. So that's our inner, which means our outer, remember, is just a little bit different. It ends up being tan. So our outer, okay, same idea. We'll have to multiply it by the million sides, just like above. It's going to be multiplied by 2r tan with the exact same angle, 0.00018. If you're not sure, you can try it yourself, but essentially it's just our 18 divided by 100,000, okay? Because we have a million being 100,000 times larger than 10. Okay, so set up our inequality again. 2 pi r has to be less than our million. So I'm going to call our 1 million times 2r10, 0.00018, we'll fit that in, and 1 million for our inner times 2r, no, sine 0.00018. So we divide by our 2 and r, it eliminates our 2r again and 2r again, and we're left with just a million times sine to this angle. So let's figure out exactly what this is. And this should give us a very accurate number for sine. I think it should give us accuracy up to like about 12 decimal places. So that's 0.00018 for sine, so we're doing the inner, times a million. So there's 6 times. And we get 3.141592,653. 3.14. I cannot even remember that. 1592. 1592. We'll try again. 92653. 653. Okay, and I think that's the decimal place we're going to be accuracy up to. So we take 0.00018 times 10 and multiply by a million. 2, 3, 4, 5, 6. And we get 3.145926. So it's very similar. 5, 3, and 6 in this case. So it's the exact same. 3.141592653. And it actually is more accurate to these decimal places here. And this is exactly what pi is. So this is our proof that pi is definitely between those values. Are you done?